Building a quantum computer is a complex and interdisciplinary task that requires expertise in physics, engineering, computer science, and material science. Here's a step-by-step overview of the process to guide you conceptually. 1. Understand quantum computing principles. Before building a quantum computer, you need to understand the foundational concepts. 1. Qubits. The basic units of quantum information, capable of existing in superposition and entanglement. 2. Quantum gates. Operations that manipulate qubits. 3. Quantum algorithms. Algorithms like Shor's and Grover's that exploit quantum mechanics. 4. Decoherence. Loss of quantum information due to environmental interaction. 2. Choose a qubit implementation. Qubits can be realized using various physical systems, each with pros and cons. 1. Superconducting circuits. Popular in industry, used by IBM and Google. 1. Qubits are created using Josephson junctions. 2. Trapped ions. Use ions trapped in electromagnetic fields, used by IonQ. 3. Photonic qubits. Use photons as carriers of quantum information. 4. Topological qubits. Based on exotic quantum states, still experimental. 5. Spin qubits. Use the spin of electrons or nuclei. 6. Evaluate the trade-offs like scalability, coherence time, and operational complexity. 3. Design and build the hardware. A. Cryogenic environment. 1. For many systems, like superconducting qubits, operations require extremely low temperatures, millikelvin range, to minimize noise and decoherence. 2. Use a dilution refrigerator for cooling. B. Qubit fabrication. 1. Superconducting circuits. Fabricate using materials like niobium or aluminum on silicon wafers with photolithography. 2. Trapped ions. Use vacuum chambers and laser cooling to trap ions. 3. Photonic systems. Use integrated photonic circuits. C. Control systems. 1. Design high-precision electronics to control qubits, e.g., microwave pulses for superconducting qubits or lasers for trapped ions. D. Measurement systems. 1. Qubit states must be read without collapsing their quantum states prematurely. 2. Example. Use Josephson parametric amplifiers for superconducting qubits. 4. Develop error correction. Quantum systems are prone to errors due to noise. Implement 1. Quantum error correction, QEC, techniques like the surface code or Shor's code. 2. Ensure your system has sufficient physical qubits to support error-corrected logical qubits. 5. Build the software stack. A. Quantum programming language. 1. Use or develop languages like Qiskit, IBM, Cirq, Google, or others. 2. Translate high-level algorithms into quantum gate sequences. B. Quantum control software. 1. Ensure precise timing and amplitude control for quantum operations. C. Simulation and testing. 1. Simulate the quantum computer on classical systems to validate algorithms and hardware behavior. 6. Scale the system. 1. Add more qubits while maintaining coherence. 2. Design modular architectures to interconnect multiple quantum processors. 7. Test and optimize. 1. Test the system's performance using benchmarks like quantum volume. 2. Optimize the hardware and software iteratively to reduce errors and improve fidelity. 8. Address practical challenges. 1. Decoherence. Develop techniques to minimize interactions with the environment. 2. Scalability. Address wiring and control challenges for large qubit systems. 3. Stability. Maintain stable conditions in cryogenic and vacuum systems. 9. Collaborate with experts. Quantum computing requires interdisciplinary collaboration. 1. Physicists to design qubits and understand quantum phenomena. 2. Engineers to build hardware and control systems. 3. Computer scientists to develop software and algorithms. 10. Stay updated with research. Quantum computing is an evolving field. Stay informed about breakthroughs in 1. New qubit technologies, e.g., neutral atoms, topological qubits. 2. Advancements in quantum algorithms and error correction. 11. Build prototypes. 1. Start with small-scale systems, 10 qubits. 2. Gradually build more complex systems to increase computational capabilities. 12. Real-world applications. 1. Focus on practical applications like cryptography, optimization, and drug discovery. 2. Partner with industries or research institutions to explore use cases. Conclusion: building a quantum computer is a long-term endeavor requiring significant expertise, resources, and patience. While the steps outlined above provide a high-level guide, each step involves intricate details and challenges. Most progress in this field is made through collaborative research in academia, industry, and government-funded initiatives.